Okay, so we want to write an expression for the apparent nth term of the sequence. So we know the first four terms here, and we need to come up with basically the equation that would give you this sequence. The thing about getting these equations is we always assume we start with 1 for n. So unlike numbers, when we normally count, or like normal equations, you might start at 0. For sequences, we always start with 1 because the first term we say is n equals 1. So that's the difference between just the general equation and then a sequence is your starting point. So the nice thing is that you are usually always given the first term. So terms are denoted by A, is what we call a term. So the first term we know is 1/2. And trying to come up with an expression is all about finding the pattern. So this pattern is not as complicated as some other ones that you might be able to see. But if you see, the top is not changing. So if I wanted to write a sequence, an expression for the nth term, I know the top is always going to be 1 because that's what we see. So I can just kind of fill that in. The other thing that I can notice here is that this one is changing from a positive to a negative. So whenever we have sequences that change from positive to negative, that generally means we're always multiplying by -1 to a power. And then you just need to make sure that the exponent is going to give you the correct positive or negative. So I'm going to actually change my 1 up there. And I can change this to a -1. And let's say we have -1 to the n. If I have n equals 1, I'm going to get a negative out because -1 to the first power is negative. Our first term, however, is positive. So the way to get around this is either to do n-1 or n+1. It doesn't matter which way. So I mean, either by adding 1 or -1, you'll get the same thing. So if I wrote that instead as n+1, and then I plug in n equals 1, that would be an exponent of 2. Squaring a -1 gives me a +1, and then I get my correct 1 for a 1 equals 1/2. The second term we have is -1/4. Now let's say I just put that negative up with the top of the -1. Oops, this is not a to the n. That's the second term. So n is equal to 2 for that second term. So if I plug into what I have here, my exponent would be 3. So -1 to the third power gives me a -1. So now I know that that matches. So I can double check for the third term and the fourth term, but I've figured out my plus and minus switching. Okay, I knew it was going to be 1, and then I'm like, wait, now I need to take care of a negative, and then having to kind of plug in some numbers and say, okay, this is not quite right. How do I modify this to get the right number that I want? So now we've got the plus or minus 1 taken care of, and we have to look at the denominator. So the denominator, we have 2, and then we have for the second term 4, which is actually 2 squared. Third term, we have 1/8. So the denominator is 8, which is actually 2 to the third. So if you notice that pattern there, you see, oh, my denominator is powers of 2. A to the fourth is a -1 over 16, and 2 to the fourth is equal to 16. So by noticing that pattern in the denominator, I can fill in the denominator of my expression as 2 to the n. So when n is equal to 1, the denominator is 1. N is equal to 2, the denominator is 2 squared, or 4. N equals 3, then I get 8. So that matches what we have. So I have now taken care of my negative sign, I've taken care of the 1, and now I've taken care of the denominator. So now this is the correct expression. Should have kind of given me a little more space, but that's the correct expression for this sequence. And I had to just kind of do some looking at the patterns and then checking, okay, how do we get our signs? Let's move on to a more complicated one, because as I said, this one's not too bad. It's just you've just got the plus and minus going on, and then you just have that denominator. This one here, there's a lot more going on here. And so this is one where you really have to figure out, okay, what's really going on? So I'm going to just rewrite my terms here. And what's really nice is I've written this as 2 over 1. Usually they'll just give it to you as 2, and then you have to say, okay, well, let me write it over a fraction like the other ones. So I've got 2 over 1. The second one is 6 over 3. Third one, 24 over 7. And notice that these are not reduced either. If they were reduced, it'd be even harder to find the pattern, because then you would have to figure out, well, what reduced in order to get what I had. So these are not reduced on purpose so that it's a little easier to figure out the pattern. So I'm going to start with the top, and then I'm going to start from the bottom. I'm going to give myself a little more space here. I'm going to write a fraction. So I start with my first term, A1, and I have a 2 on top. So I'm going to just put that 2. Now let's try to figure out what's going on next. I've got 6 as my next term in the second term. The numerator is now 6. So that could be multiplying by 3. So let's say I said, okay, this was 2 times 3. Now I have to make sure that that only shows up on the second term, because if I have it as it's written, 2 times 3, if n is equal to 1, I get 6 on top, but I only want 2 on top. So what I could do is say, okay, we can do an n minus 1 deal. When n is equal to 1, that would be 1 minus 1, which is 0, and we're not multiplying by 3. But when n is equal to 2, 2 minus 1 is 1, we're now multiplying by 3. And we would get 6 on the top of our fraction. So now I want to test this out. Does this work for n equals 3? Do I get 24? So 3 in the numerator, or as for n, we'd have n minus 1, which is 2. We get 3 squared, which is 9, and then 9 times 2, which is 18, not 24. So I came up with something for the first term, then I came up with something for the second term. I tried it on the third term, and it doesn't work. So we have to think about this differently. There's something else going on here, because with this current pattern that I wrote, I would get 18 in the numerator, not 24. So this is sort of the thinking process that you have to go. You basically have to guess, try it out, and see what happens. So does anybody have any ideas right now? Any thoughts on maybe what we could try? This is sort of, I mean, there's no wrong answers. You have to, aha, Alicia says factorials. So when I picked these problems, I haven't actually solved these because I wanted to emulate the process. So I actually don't know what it's supposed to be, but that would be my next thought. Because if we have 2 times 3, which is 6, and then if we multiplied by 4, that gives us our 24. So that does start to think we might have to use factorials. So let's start over and let's kind of think about this. And I'm going to do this in, oops. I have a student calling me right now. Well, I'm a little busy. And it popped up on my screen. You guys, it didn't pop up on your screen though. Okay, so let's think about this as factorials. Let's say this is 2 factorial. 6 would be 3 times 2 times 1, or basically 3 factorial. 24 is 4 times 3 times 2, so that is 4 factorial. So notice whatever n is, the factorial is 1 more than that. So when n is equal to 1, we had 1 plus 1, or 2 factorial. When n is equal to 2, we have 3 factorial. So notice that pattern, it's going to be n plus 1 factorial. So to test that out, for 4, we want 5 factorial. So I'm going to do that on my calculator. And that gives me 120. So then we should double check to see that it works for the next term. When n is 5, that would be 6 factorial. And that's 720. So that was a great idea, Alicia. That was what we needed to do. So we have now found the top. Now we have to figure out the denominator, what's going on in the denominator. So I'm looking at this denominator. It does not look like there's multiplication going on here, because we're going from 1 to 3 to 7 to 15. This looks like it's an adding deal, perhaps. So then I would start looking, well, what am I adding each time? How much am I, what is it changing by? And maybe you've already thought about this. So maybe if you figured it out, you feel free to put it in the chat. Adding 2 to the nth power. All right, so let's see. So let's test this out. So we would start with 1 there. And we don't want to if we just do straight 2 to the nth power, when n is equal to 1, that's going to give us 3. So let's try subtracting. No, we don't want to subtract 1, because when n is equal to 1, that would be 2 to the 0, which is 1. We get 1 plus 1, which is 2. So we have to think about something here. We're thinking 2 to the nth power, because like from 1 to 3 in our denominator here. Let me do this over here. 2 is added. That makes sense. 3 to 7, we're adding 4. So you can definitely see the nth power going on. 7 to 15, you add 8. And I'm assuming 16, yes. Add 16, that gives you 32. So that 2 to the nth power is great. We just have to figure out where we're starting at. Because how I wrote it right now doesn't work. So I'm going to try something else. Let's see. We're adding 2 to the nth power each time. I'm thinking through this. If we just do 2 to the nth, that doesn't work. So if you guys have ideas, feel free to try them, and we can try it out. Because I'm thinking through this as well. I'm thinking, we know we have to have 1 in the denominator. And then we're adding, let's see. I just thought of something. What if I did 2 to the n minus 1? I kind of flip-flopped it. If n is equal to 1, we get 2 minus 1, which is 1. So we have our denominator of 1. If n is equal to 2, we get 2 squared. So that's 4 minus 1, that gets us 3. So n equals 3, 2 to the third is 8, minus 1, that gets us 7. 2 to the fourth, 16 minus 1 is 15. And then 2 to the fifth is 32, minus 1 is 31. So these are changing by 2 to the nth power, but just writing what was going on wasn't quite working out. And if we flip-flop it, we actually get it to work. If we do 2 to the nth minus 1. Do you guys see how that works out there? one trick with these things, and this is a little trick that you see when you do these often enough, is that sometimes if the adding doesn't work, try subtracting, try reversing it, because this is something that actually comes up a lot, this doing something to an exponent and then subtracting 1. So that's why I thought about it. I'm like, wait, let's try this trick. But you have to do enough of these things to try it out. We knew the 2 to the n was the key. It was just, how do we make this work out? Maybe we need to try to go about this a different direction. Are there any questions on this one? Okay. So I have a couple more where these are also involved with the sum. And so in these particular ones, we want to write sigma notation to write the sum. And in order to write the sum, you have to first figure out the sequence pattern for the nth term, and then you plug that into the sum. So each of these we're going to treat as a part of the sequence. So you just want to ignore the pluses for now. Ignore the sum part because we still have to figure out what we want. And we don't know, I don't know what term that final term is. I don't know what n is. So I'm just going to put a question mark there. We need to use the first 3 terms to find the pattern, and then you can figure it out. Now this one's actually quite simple one. So I'm sure that you can look at this and see that the pattern is we have 5 on top, we have 1 plus, and then it looks very clearly that each term you're just adding n, 1 plus n. So 1 plus 1, then 1 plus 2, plus 1 plus 3. And so following this pattern, that means this last term is n equals 15. So this is a very simple one first, just to kind of get you into the thought process. Well, if we're going to write a sum just from a pattern that we have here, we have to determine the pattern first. So then we want to take this and turn it into sigma notation. So I have my sigma. Sigma is a Greek letter. I think it's literally the Greek S. And we usually have I instead of n. I'm not sure why we do that when it's summation notation, that we use I instead of n. But again, we start with 1, and then at the top is where you stop counting. So we're counting up to 15. We're going from the first term to the 15th term. And then what we found for a to the n, that is what is in our notation. We just change all n's to I. And so that is our sigma notation here. That we're adding all of those terms, and we're adding them up from 1 to 15. Are there any questions? Okay. Now this one is going to be a little trickier. This is because, I mean, there's more going on here. Again, I'm going to just label each of these. This is the first term. This is the second term. This is the third term, and then we don't know what term this is. So we have to kind of figure out what's going on with the first 3 terms to determine our notation. So we have to find the nth term. Now the tops are 1, so that's easy enough. So I'm not going to, I'm looking at this and I can tell basically immediately what my denominator is going to be, but I want you guys to try to figure this out. So what does it look like the pattern would be for the denominator to get the pattern that we have? Okay, a times a plus 2, I plus 1. So we got one with addition and one with multiplication. So let's see. So if we had a as 1, if that was 1 times 1 plus 2, so that'd be 1 times 3. And the other one, 1 plus 2, that would be 3. So that would be adding. So Alicia, yours looks like 2 plus 3, not plus. Okay. Yeah, probably meant like multiplication there. So Tim's is actually what we want, and I'm going to use n. So we have n and then times n plus 2. So you notice that our first term, if n is 1, then n plus 2 is 3. So we got 1 times 3. Or the second term, n is 2, we have 2, and then 2 plus 1 is 4, so 2 times 4. And we have 3. 3 plus 2 is 5, 3 times 5. So that's our pattern here. It's n times n plus 2, which means that based off of that pattern, our last term here must be 10, because it's 10 times 12. So I can label that as a sub 10. So now that we've figured out what the pattern is, to put this in summation notation, again, I'm going to write my sigma. And now I'm going to make them i's, and we always start from 1, and we're going to count up to 10. And then I need to convert all of these n's to i's. So it's 1 over I times I plus 2. And that is our sigma notation. Any questions? Okay, so those are my examples where we have to basically take a pattern and then try to figure out what the pattern is. Something that I think a lot of people get stuck in is finding the sum of an infinite series when you're not given a formula. So I'm going to skip to that one here. So if you go on and read the rest of the chapters, like 9.2 and 9.3, for certain types of sequences, there is a formula. There's a formula for infinite sums of an arithmetic sequence, and there's a formula for infinite sums of a geometric sequence. There's no formula for other sequences. Those are the two main types that we actually have a formula to determine the sum. If it's not one of those types of sequences, then we determine the sum another way, and by kind of guessing where does it look like it's going, essentially. So here we've got a sum of an infinite series, because it goes to infinity, of 2 over 10 to the I. So when you don't have a specific formula, you basically just start plugging in numbers to determine where does it seem like it's going. So let's first do one term. If we're only counting to 1, we're doing the sum of the first term, I is equal to 1. We would have 2 over 10 to the first power, 2/10, which I'm going to just write as a decimal for ease. It's 0.2. Now, what if instead of going to 1, we wanted to count the first 2 terms? So that would be 2 over 10 plus 2 over 10 squared, because the second term, I, is equal to 2. So I'm going to just do that in my calculator because I can, and write it as a decimal, 0.22. So now we want to try, okay, we'll try adding up the first 3 terms to see what happens. So we're still adding up 2 to 10 to the I, but now we want the first 3 terms. So we've got 2 over 10 plus 2 over 10 squared plus 2 over 10 to the 3rd power. So I'm going to add that into my calculator. I get 0.222. So do you see the pattern that is starting to develop here? It seems that each of these I'm adding another decimal place of a 2. So if you're following this pattern, then presumably if we do this to infinity, this would be 0.222, like the 2's would just keep repeating on. Because if you follow that pattern and you assume, okay, it's going to keep continuing. So we don't like to write our answers as decimals if we can convert them to a fraction. So you may not know this fraction, but if you do you happen to know what fraction is basically 0.2 repeating? Two ninths. Alicia, that's correct. So this means that based off of this pattern, we can tell that it's going to just go on forever with adding 2's. So this series adds to 2 ninths. And so even though it goes on forever, we can say with confidence here that the sum of this infinite series is an actual number, and it's 2 ninths. And we do this by just kind of following the pattern and then saying, okay, if this pattern continues forever, what do we have? When a series has a sum like this, there's an actual number it adds to, we say that the series converges. If there's no sum, we say it diverges. So this is a convergent series because it actually has a single number that it adds up to. Another way to look at this is there's a concept in calculus, which you guys have to take after this class. If you're an engineer, and I don't think computer science has to take calculus. Maybe you do. But there's a concept in calculus called the limit. And it's something that you've actually seen in algebra. When you talk about asymptotes, those are actually limits. But the limit is basically, as you go to infinity, what happens to your pattern or your graph or your numbers. So as we go to infinity with this series, our numbers are approaching 2 ninths. So we can also say that the limit is 2 ninths in this case. This concept of a limit is what happens when you go towards infinity, what happens to your pattern, essentially. So this is how a lot of sums of infinite series are found. There are actually other methods that you can use to find the sum of an infinite series. And actually, I am going to pull up YouTube. One of my favorite YouTube channels has a few videos about series. So it's Numberphile. So I'm going to just click on their channel here. I don't know if it's under a specific playlist that they have. They have a lot of great stuff. Let's see. I know they have things about series. So I've watched some of these. Oh, I wish I remembered the name of it. They have just so many videos. It was all about adding up alternating ones. It might be easier if I just find this on my own, or if I search third channel for like alternating ones or something. Or maybe I'll just search for sequence. A bunch of different sequences. Well, here's a good one that might help you. Oh, you found it! You're faster than I was. They have one here, and what number comes next? So that's a good one to practice with trying to come up with these things. Let's see, is this the one that I was thinking about? Yes, this is the video. Thank you, Alicia. This is exactly the video I was thinking of. 1 minus 1 plus 1 minus 1. And it talks about that pattern and what does that sum equal. And it's pretty mind-blowing what the sum equals. It's crazy. And here's another one here. This is a different channel that I really like, 3 blue, 1 brown, where it has a series, and you can see it on the thumbnail, that somehow magically comes out to pi squared over 6. These infinite series things are crazy because you look at, let me go back to the one that we had. If you asked me what this added up to, I would not immediately think it's going to be 2/9 because the number itself looks like, well, 2 over 10, that's 1/5. You know, you would think, okay, maybe 1/5 plus 1/5, and you would almost think that it would add up to infinity or something like that. Or if anything, it would add up to something with a fifth. You wouldn't necessarily think, oh, this actually adds up to a number 2 over 9. Infinite series are nuts, and they come out to things you may not expect, like this pi over 6, pi squared over 6 kind of thing. So if you're really interested in knowing more and seeing some of the tricks for finding these things and finding out what the sums are, I recommend checking out some of those videos. I should share those in a YouTube or like on an announcement or something. I think that would be very helpful. Kind of fun. It's really fascinating. And studying this kind of thing, it's part of pure mathematics. There's also a part of math where you focus on like permutations and sequences and series and all that kind of stuff. Combinatorics usually relates to a lot of these things, so that's a different area of math where you can talk about these things. Let's see, let's take a look at this problem. I was looking at the examples that I have, and I think this is a good kind of mind bender kind of thing. As I said before, I picked these out of the text. I actually haven't done any of these problems because I wanted to kind of go through the same problem-solving thought process that I have to kind of model it for you guys, so we can kind of, you can learn the thought process together and how you think about how to solve these kinds of things. Same sort of thing that I want you to do in the journals is like, well, how did I come up with this? What am I thinking about? So let's take a look at this one. We've got factorials going on. We have 2n minus 1 over 2n plus 1. And there's a factorial on the top, factorial on the bottom. And we're asked to simplify this. And your first thought is probably, well, what do I do? We can't cancel out the 2 n's because we have this plus and minus going on. It's what I like to call legal algebra. We can't just cancel those out because they're inside something with a plus and a minus. So another thing is sometimes people might do is, well, let me try this with numbers and see what happens. And that's a good way to kind of get an idea of the pattern. But let's not do it with numbers. Let's actually take a look using just the definitions that we know, which is the definition of a factorial. So let's just try rewriting this. So a factorial means you basically take what you're doing with that factorial and then you're subtracting 1 each time. So like the numerator, I 2n minus 1, and then my next term, I subtract 1 from that. So 2n minus 1 minus 1, and then we would subtract 1 again from that. So you can see we keep subtracting 1, and then that's going to keep going, and then we end up as 1 as our final number. And with the way that the factorial goes, we're eventually going to end up with 3 times 2 times 1, because it will go eventually down to those numbers. So let's do the same thing in the denominator. The denominator will be 2n plus 1 factorial. So 2n plus 1. Then we're going to subtract 1 by plus 1 and then minus 1. And I need to subtract 1 again. And then again, I don't know how many I'm going to have, but I'm eventually going to go down to 3 times 2 times 1 there for a factorial. So you can see immediately, just by me kind of rewriting this, that we are going to have a lot of things cancel out, because that's the nature of factorials. You're going to have things cancel, things on the top, things on the bottom. And that's what kind of makes them nice when they're in a fraction, because they simplify nicely. I'm going to simplify all of my subtracting ones kind of things so I can rewrite these algebraically. So I have 2n minus 1. And then I have 2n minus 2, 2n minus 3, and then we know that eventually we're going to get down to, make sure that's not looking like a decimal, 3 times 2 times 1. And then the denominator, 2n plus, whoops, I lost my n, 2n plus 1. And then 2n plus 1 minus 1, so then that's just 2n. And then plus 1 minus 1, we end up with 2n minus 1. And then if I kept going, keep subtracting 1, I get 2n minus 2, 2n minus 3. And you can see that now we're starting to get to where we repeat. I'm going to draw my line out there. So we're just expanding our factorial and using the definition that you're subtracting 1 each time. And I subtracted 1 enough times in the denominator so you can start seeing where the repeats are. So you can start seeing where things cancel out. So I have a 2n minus 1, 2n minus 1, 2n minus 2, 2n minus 2, 2n minus 3. And basically everything else is going to cancel out. So on the top, we end up with everything canceled out, so we end up with 1. And then in the denominator, we end up with 2n plus 1 times 2n. And that is how this factorial expression simplified. And that sort of actually gives us a formula to do a factorial like that if it's in that form. Next week, we are going to be learning about probabilities, combinatorics, things with factorials. Again, we're going to do combinations and permutations. And there are formulas for those, and those actually come from patterns like this. The formulas to, even in some of these infinite sums we talk about this week, come from some of this idea where it eventually simplifies to something like this. What we just did here is something that a lot of mathematicians do, is they're basically like, oh, let's see what this simplifies to. Does this give me a formula I can use? And maybe they don't use the formula, but it's like just playing around with math, seeing how does it simplify, what do I get? That's really what pure math is all about, is just taking things with formulas, following your rules, and seeing what your outcome is. So this is a perfect example of what like an actual mathematician does, as they're just like, let me see what happens when I simplify this. Oh, that's cool. This gives you an idea of like sort of mathematical thinking as well, is when you're seeing something like this, you're like, okay, what rules do I know? What definitions do I know? Let me apply those. And that thinking is good in other fields, in computer science. How do I know things work? Let me see what happens if I apply that. In engineering, for sure, you have all these definitions, and you might be trying to solve a circuit, and you're like, well, what do I know about this circuit? Let me play around, see what happens. That's sort of what mathematical thinking brings to the table. And like you saw with the the sequences, we're trying to find the pattern. It's kind of like, let me play around, see what works. I mean, that's really sort of what math is you're exploring things by just trial and error and just using rules that you know, try it out, see what happens. I know I've kind of gone on a rant about math here. I mean, I think this stuff is so cool. Do you guys have any questions on this particular example? Are there any other things about like sequences and series that you might need more guidance on, something that you know might want to see more examples on? Because I have tons of examples of the simpler stuff where you just plug in numbers for n. If you want to see those, I can totally do that. Or we can say we've been here 45 minutes. We can call this good. So it's up to you guys and what you think you need to see more of. Okay, Alicia, you don't have anything. I think I went over the hardest problems anyway. So, oh, here's something that I should show you guys. So, graphing sequences. Sometimes graphing helps you visualize them, and it might be something to help you visualize for like the discussion this week. When we graph a sequence, you're graphing just ordered pairs because it's a distinct set of numbers, like a first term, second term, third term. We don't have like one half term. So I do have a link in this PowerPoint, and when I share out this video, I'll include the PowerPoint showing how you can graph these in Desmos. So let's see if I can actually get this to open. So this might be helpful if you want to kind of check your work. So basically n is just how many, do you want the first 5 terms? We don't really have whole number decimal terms. Let's say we want 30 terms, and then you can put in the sequence here. So let's say instead of a sequence like this, my sequence had 2. And this just shows you what your values would be if you had a sequence like this. And let's say I put a number in front of here and I changed my sequence. Or, I don't know, this is going to be really gross, probably. I don't even know what this is going to look like. Okay, so it's going down, just what I happen to do. But if you want to see the sequences you wrote and like double check that your numbers are right, you can use this Desmos plot for that, and then it'll plot each term of the sequence. There's also one, it might be under the examples here. Let's see. No, it doesn't look like it's under the examples. I thought that Desmos had one under the examples for the sum of a series where it would figure out the sum. But Desmos actually allows you to type that in. So if I wanted to find the sum of this sequence, that I can go to my keyboard here and go to functions. What is it under? It's under miscellaneous here. And you can see that we've got this sum symbol. So then you would say, okay, let's say I want to count the sum of the first 30 terms, or no, I want to start at 1 and then go up to 30. I have to hit my arrows to get up there. And then let's say I'm going to use that sequence that I did, A of, let's do N. And then I should give me, okay, I didn't like that. What if I did A of X, because that's what we called it. I've done this before. Maybe I have to actually type in the sequence. So I'll just copy and paste it. If it gives me, what is it not liking? Oh, I can't use N. What if I made these I's? Maybe I want to make this an I. There, nope. I've try adding Y equals, okay. I've gotten this to work before, but I don't remember how. Y equals, now that just gave me an equation. I'll have to play around with this. I don't remember how to do it, but I know there is some way to find the sum of a sequence in Desmos. Clearly, I am not figuring out what that way is. So, I was going to show you if I could figure it out so you can like check your work, but I'm not exactly sure why it's not working. I don't know if it's this particular sequence that it doesn't like, or if I'm just doing something else wrong. But anyway, I think that's probably good. So we've got a wide variety of things directly related to the text, outside pieces of information. But hopefully this was helpful. I'm going to send out this recording as soon as it processes.